Hey everyone! New section for us today. Section 15.7. This is going to be on triple integrals done in cylindrical coordinates. But before I jump into whatever cylindrical coordinates are, I wanted to do a brief recap on triple integrals. Now, hopefully, if you're watching this video, you've already seen the one for 15.6 on triple integrals. At any rate, some highlights from that section that we're going to need to dust off for today are the following. First off, whenever I express an integral that looks like this guy, it's got these three integral symbols over some sort of region E. I've got my function named and this weird dv differential on the end. What that dv differential meant was we're integrating with respect to a volume, so whatever region that you're specifying to integrate over, E here, that should be a 3D shape of some sort. And whenever we have one of these integrals to evaluate it, well, first off, we need to actually do something with dv, express it in some sort of combination of dx, dy, and dz. Now you could use this order, you could do dz, dy, dx, you could do whatever was appropriate for your region, as long as you set up your bounds matching these variables appropriately. Now, some restrictions on this that we mentioned last time were that for general regions, you can have variables stuck between different functions instead of just constants. So if you did happen to have a variable that you saw as stuck between two surfaces, well, surfaces are functions, well, basically they're graphs of functions of two variables. So if you have a function of two variables in one of your bounds, that's going to have to go on the very, very inside. If you take care of that integral and consider the projection down to the remaining plane, well, whatever remaining bounds you should have there should be expressible as curves of some sort. Those would need to go in your middle variable. And then finally, your outside bounds should be constants. Okay, so regardless of however you set this up, dz, dy, dx, dx, dy, whatever, you should have numerical bounds on the very, very outside. Now, final reminder for us, another thing that I mentioned, handy dandy way to measure pretty much any region object that we're going to talk about in this class. Take an integral of 1 with respect to the appropriate differential. So here, if I wanted to measure the volume of a three-dimensional region E, well, I integrate 1 with respect to volume over that region. Okay, so let's try a somewhat simple-ish example to dust this off. I'm going to request that we use a triple integral to find the volume of a cylinder with height h and radius r0. Now, this is not automatically set up with functions or whatever. I know I promised that this was going to be relatively simple, but this isn't too bad of a problem to set up. Basically what it's suggesting is we have to come up with what functions we're looking for to build this cylinder in the first place. Now, let's think about this. It's kind of like physics. Since I've given us a lot of leeway here, we get to pick our reference frame. What I will suggest that we do to demonstrate the volume of a cylinder formula is basically this. I will give us, if I have a pen to draw here, I will give us a cylinder, okay, it's lying flat on one side here, and I'm going to let the height of this thing be measured along the z-axis. Okay, so we'll pretend this is our nice, neat little cylinder here, with my xy plane down below, height of this thing measured with respect to the z-axis. Okay, now, first off, if I want to think about what's going on with my height and my radius, I am trying to spell out that, the height of this thing should be h. If I'm saying that the radius is r0, that value there should be r0. This value here should also be r0. So that should be some sort of a circle of radius r0 centered at the origin here. And I'm going to go ahead, and since this cylinder should have height h, well, cylinders are going to be flat on the top. I'm going to assume that's a plane that is sitting on the very, very top here. And if we wanted to make sure that this was a horizontal plane that was of height h, well, that plane is going to be z equals h, whatever number h happened to be. Okay? So, if I want to figure out the volume of this thing, well, we already mentioned this above. My volume should be a triple integral of 1 with respect to volume, and I just have to make sure that I take this over the appropriate region. Okay, so this thing that I set up here, that was me trying to describe this region E that we needed to integrate over. Now, the usual way that I feel like most people tend to be comfortable with setting these things up first is figuring out your bounds on Z. Treat those as being stuck between, two surfaces. So if I wanted to sort out my bounds on Z, well, really I'm asking myself, how far up and down can Z go? Well, I can't imagine that top surface of the cylinder, that plane Z equals H, is one of my bounding surfaces. I can imagine that the XY plane, or this is the same thing as the plane Z equals 0, that is the bottom bound on my surfaces. Well, that means that I could think about sticking Z between 0 and H. Okay? Now, once I go ahead and do that, you need to figure out the bounds on X and Y. Well, for us to do that, you have to think about the projection down to the XY plane. If I were to shine a flashlight parallel to the Z axis, okay, whatever this first variable I tackled was, if I shine a flashlight parallel to that axis on my region and think about what sort of shadow it would cause on the XY plane, well, it's that red shaded region that I drew below. That's what we get to focus on to figure out my bounds on X and Y. So what I want to think about here is, if I convert this to, hopefully that's a circle, okay, shine that flashlight on the cylinder in that orientation, you get a circle. This should be a circle that we specified was of radius r0, okay? So this is the region that I need to use to sort out my bounds on X and Y. Well, how do I do that? Well, I feel like, again, most people tend to be comfortable thinking about setting this up as a type 1 region. That means that we would have y stuck between two functions, this top function here and this bottom function down here. And then we would probably stick x between two numbers. That part's probably pretty easy to sort out. We can stick this between minus r0 and r0. We know what the radius is. Okay, so we know how far this goes in the x direction. Just what are these functions? Well, if this thing has radius r0, this is going to be, my circle equation, x squared plus y squared is r0 squared. If you go to solve for y in this, you get both of your functions back, right? We'll get plus or minus square root of r0 squared minus x, wrong pen stroke here, minus x squared. So those are going to give me my top and bottom bounds. In other words, if I want my bounds on y and on x, what I am expecting to get here is we have y stuck between this minus r0 squared, minus x squared function, and the positive version of that same function. And again, like I mentioned a moment ago, we have my x stuck between minus r0 and r0. Again, if I wanted to set up and evaluate this thing, okay, the goal was to figure out the volume of that cylinder. We are trying to rewrite this volume integral. That just means that I need to actually piece all of this stuff together, right? So what am I integrating 1 with respect to? Well, we sorted out my bounds on z first. I'm going to go ahead and stick those here. So we did dz first. The next thing that we sorted out was y. Here's my minus square root function and my positive square root function. Okay, so that was my bounds on y. And then finally, my bounds on x is the very last thing that we took care of. We went from minus r0 to r0. Okay, now some comments here. I know some of you guys may be like, oh, well, we said that the function bounds have to go on the inside. Why didn't we do that? You know, we only have these like two, if I'd started out with a constant height for the cylinder, we only have these two constants in the middle. Well, we did technically view those as giving us surfaces for a region. It's just that, you know, the surfaces that we had were based on constant functions. So we can still technically view those inner two functions as functions of two variables. It's just that we got constants back. At the very least, if you did want to do the functions the other way around, you know, if you wanted to swap dz and dy here and, you know, flip those around, that would be totally okay in this one particular case, because, you know, functions do have to be towards the inside, but don't freak out too much about these guys being inner bounds. We just have constant functions of two variables instead of, you know, things that actually have x's and y's and whatnot in them. Okay? Now, with that said, if I actually want to evaluate this, I will point out, before actually making us do this, because this actually looks pretty messy, we are running into a very similar case to what we saw at the introduction to the polar integrals section. Now, in the polar integral section, I mentioned if you integrate over something that looks round a lot like this guy right here, okay, this region that I'm... Yes, Kepler. Sorry about my cat. If you're integrating over a region that's round, those are integrals that tend to get to be a pain in the butt really, really fast. You know, foreshadowing for this integral, if you did feel like trying it out on your own, we're going to get to a part where you end up having to do trig substitution once you start dealing with these pesky square roots here. And it'd be nice if we didn't have to do that, if we could view a round integral in a simpler manner. Now, I did bring up polar integrals, but polar integrals were a way that we could fix double integrals, and this thing here is a triple integral, so what do we get to do, right? My big motivation for today. What if we find bounds, you know, on Z, set up my integral, go to integrate this thing, and then when we're dealing with our projection region, what if it's round, like what we were dealing with in the polar integrals section? Now, what that kind of boils down to is I'm asking this question, what if E is kind of at least partially round? You know, we dealt with this cylinder before. It was flat on top, so it wasn't round everywhere, but it's at least round on the sides. Okay, what if I run into a region like that? Well, the idea is we actually do kind of want to steal some concepts from that polar coordinates section, right? So we still kind of want to steal the ideas, okay, from polar coordinates. We do want to end up rewriting our integral, but what that's going to have us do is we still have to take this integral that we are starting with, our initial, you know, triple integral, whatever we ended up worrying about that was over this round region, and once we had that integral, we have three things to fix now, but they are potentially going to be different things from our polar section. We now have a three-dimensional region instead of a two-dimensional one. We now have a function of three variables instead of a function of two, and we now have a totally different differential to worry about, right? So if we take that triple integral, we still have to fix the bounds, the function, and the differential. It's just that there are different things that we have to fix, so we have to adjust accordingly, right? So still have to fix my bounds, my function, and my differential. Okay? Now, how the heck do I actually do that? Well, I'm going to scroll down here and make some comments on how we get going with our cylindrical integrals, right? I mentioned the very first thing that we want to do is fix the bounds. I am going to tackle that here with points 1a and 1b because we kind of have two different pieces in which we have to consider how we go about fixing my bounds. Since I have these cylindrical integrals, first off, I am going to make an assumption here I'm going to make the assumption that my dv is best set up as either dz dy dx or dz dx dy. And one of the things that that's going to do is if you set up your integral in one of these manners, it means that z is the function, or z is the variable that is stuck between two surfaces. So that means we probably have this set up here, right? If we are starting out with z being stuck between two surfaces, as you would in this case where z is the first variable you take a crack at, if we're starting with this, we have to find a way to rewrite those bounds, okay? The idea here was once we project to this xy region, all that stuff is going to be round. We kind of want to take a crack at that like polar, but we already know how to handle the polar stuff. We need a new way to handle z. So what I'm going to do with those z bounds is I will go ahead and replace each instance of x with, well, the expected r cosine theta, and my y with r sine theta. Okay, so this is actually nothing new. This is straight up our polar coordinates. We've seen that in the previous section. I'm not having you learn a new identity here. It's just that we're using those same replacements in my bounds. Okay, so each time that you see function bounds on z, make those appropriate rewrites. Or as a shortcut, another thing that you can use to substitute if you do happen to see it. This was another good trick. If you saw x squared plus y squared, you can crank through all the simplifications on your own, or you can just remember that that's going to end up simplifying to r squared. That's kind of a shortcut that we could use to replace those bounds. Now, the other thing that we would need to do to replace my bounds is sorting out what's going on with x and y. Well, there you have to determine the bounds on your projection to the xy plane. Here I don't really have a handy shortcut. This is actually going to be a lot similar to the polar section. Okay, so to my polar integrals section. Sketching is going to be your best tool here. So sketching helps. What's probably going to happen if I am bothering to give you an integral that's written best in cylindrical, you should probably be able to get a feel for what that region looks like. If it looks like that region is round, if it looks like it's a disk or an annulus or a pie slice, we are probably going to want to express this in terms of polar intervals. Basically just find a way to express my region in polar, do I have room here? Polar intervals. Now, if you do that, that takes care of the bounds. I said that the next thing that we end up having to fix is my function. Well, again, I'm not really having you do new identities here. We still want to replace x with, it's no longer an x, it's going to be an r cosine theta. And I no longer want to see y's, I want to see r sine thetas. Now, that takes care of my x and y. We actually don't have to do anything with z, okay? So I'm assuming z kind of gets to stay put. You know, we had mentioned that the projection is the thing that looks round, so really the xy region is what looks round. We don't need to have any other restrictions on z. We're not going to make any changes there, okay? So basically, substitute out, rewrite your function by swapping out all your x's and y's for r cosine theta and r sine theta. And then finally, the last thing that we needed to do after fixing bounds and function was we needed to fix our differential on the end. This is all there is to it. If you go to fix your differential, this is going to be r dz dr d theta. Okay, so you could rewrite dz dx dy or dz dy dx or dv with this expression right here. Okay, now kind of the same deal as for when we were talking about polar integrals. We replaced dA with r dr d theta. So this at least should look pretty familiar. And hopefully this makes sense, because if I think about dv as kind of being a little bit like dz dy dx or dz dx dy, it kind of looks a little bit like dz times dA here. Okay, and you'll notice that we have kind of the necessary components here if I wanted to think about how we did the swap in polar, right? We still have a dz in both of these places, and we said that we could replace dA with r dr d theta. Okay, so we can replace dA with r dr d theta. Okay, nothing terribly new about this differential. It's just, you know, we're adding a dz in, okay, to both sides of the equation here. Now, let's actually see this in practice. I know it's one thing to talk about the theory, it's another thing to actually do this as an example. I'm going to have us do that same cylinder problem and see if we can get it to crank out a little bit easier. Okay? Use triple integral to find the volume of the cylinder with height h and radius r0. Okay, so same exact cylinder that I was dealing with in the initial problem. Okay, this guy right here, that I'm assuming is of height h, so that this top bit was the plane z equals h. And if this is of radius r0, okay, these guys are both r0 units out from the origin. Now, again, we said that my volume, okay, the integral that I am starting with, this is supposed to be some sort of, you know, integral of 1 over the region that I'm interested in, right? So my volume of E, okay, if this thing is still E here, my volume of E is the triple integral over E of 1. Now, what I need to do if I want to express this using cylindrical coordinates is fix my bounds, fix my function, fix my differential. Okay? Now, first off, my bounds on z, right? We already decided that z was supposed to be stuck between 0 and h. Now, comments here, I don't see any x's or y's, so actually this is a pretty fast one to fix. There's no x's or y's to replace, so this actually stays the same. Okay, so this guy stays put. The next thing that I needed to take care of was, okay, step 1b that I gave you was figure out what my projection to the xy plane looks like. Okay, what region am I dealing with when I project this thing down, and how do I express that as a polar region? Okay, expressing this as a polar region means that I'm no longer worried about bounds on x and y, I am worried about bounds on r and theta. Now, if I worry about r here, r is just what radius we go out from the origin. I told you guys the cylinder was radius r0, so I am assuming that r goes all the way from the origin out to the bounds of the circle. R has to be stuck between 0 and r0. Okay, and as far as theta goes, theta, okay, if you remember from our polar section or our polar coordinate section, theta was your angle off of the positive x-axis, and it turns out that we do a full sweep all the way around the origin here, so we hit all of the angles between 0 and 2 pi. Okay, so in this particular case, theta stuck between 0 and 2 pi. Now, that'll take care of my bounds. The next thing that I would need to do is fix my function. Okay, I'll make comments about that. This is actually pretty similar to the case where I was trying to fix my bounds on z, right? You'll notice that the integrand for this particular setup was 1, right? I'm integrating 1. If f of xyz is 1, and we said we had to fix the function by replacing all the x's and y's with r cosine theta and r sine theta, I'll go ahead and note this is similar to my bounds on z. there's actually nothing to fix, okay? If you don't see any X's or Y's here, we can leave it, okay? X's and Y's are the only things that we need to replace, okay? So, this guy also stays the same, okay? Final thing that I need to do is fix the differential. I'm going to go ahead and do this in line with the rest of my problem, but I will point out, you know, we fixed that differential, okay, by using r d z d r d theta, okay? So, let's piece all this together at once. When I fixed my function, well, there was nothing to fix. We said we'd leave it as 1. When I fixed my differential, we said that we have to tack on r dz dr d theta, and this specifies the order that I had to set up all my bounds in. My innermost variable was z. We said z was stuck between 0 and h. My next variable was r. We said that was stuck between 0 and r naught. And then finally my outer variable was theta. You said that this is stuck between 0 and 2 pi. Now if I actually wanted to crank this out, because I did ask for the formula for the volume of a cylinder, you just simplify this thing, right? We work from the inside out. That means I'm really anti-deriving r with respect to z. I'll get rz here, evaluated between z is 0 and z is h. If I actually crank that out and subtract off what happens when I plug in the top and when I plug in the bottom, well, z being h means I've got an r and an h here. Plugging in the 0, you're subtracting off nothing. So I get to worry now about my antiderivative with respect to r. In this case, h is going to act like a constant coefficient, so I'm just going to hang on to it. But anti-deriving the r is going to give me r squared over 2. Now, again, I am evaluating here between r is 0 and r is r naught. When you go to evaluate your bounds here, well, you are subtracting off that 0 again, so this is going to look like r naught squared over 2 times h. Okay? If I try to antiderive this with respect to theta, you will notice that there are no thetas here, so everything acts like a constant. This thing just looks like a big old number in the integrand here. The way that you integrate constants is you just slap one of the variable on. So I've got r squared, or r naught squared over 2 times h times theta, evaluated between theta is 0 and theta is 2 pi. When I go to substitute that in, well, r naught squared over 2 times h times 2 pi. After my cancellations here, notice I've got pi times r naught squared times h. And this is exactly what you would expect for your formula for a cylinder. Okay? Now, recap on where we're at so far. And I know this was kind of a more base example. We did cylindrical coordinates on a cylinder. So hopefully that's going to be one of the simpler examples that you would run across to demonstrate this technique. How am I going to do this on a harder integral? Well, recap first. We still have to fix my bounds, fix my function, and fix the differential. Now when you are fixing both the z bounds and your function, please remember x is our cosine theta and y is our sine theta. And when you go to fix your differential, please, 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 please do not forget this r here, okay? So your differential, when you go to fix that, r dz dr d theta, okay? Now here's kind of a harder example, right? I'm actually giving you a function to work with. This is a non-trivial function. It's not a 1 like last time. So there actually will be some stuff to fix. And I'm trying to give you some sort of region to work on. I've said that we're stuck between this, that's a mistake right here. That should not be a 0. Let me fix that real quick. Let's have this stuck between the sphere where this thing is equal to 4. That was a pretty crappy sphere before. It was just the point at the origin. But at any rate, let's have a better E region here. We're stuck between a sphere, the XY plane, and a cylinder. Okay, so draw each of these piece by piece so we can kind of get a feel for what this region looks like. This sphere, x squared plus y squared plus z squared is 4. The fact that all of these are solo quadratic terms suggests that my center is at the origin. That 4 on the end suggests that we are of radius 2. Okay, so that is one piece in this solid. This thing is bounded below by the xy plane. So what's happening here is the xy plane, that flat region on the bottom, I'm going to assume that that's one of my surfaces. So that's going to at least cut my sphere in half. And then another thing that I'm worried about is the cylinder x squared plus y squared is 1. Well, if I was just dealing with the xy plane, x squared plus y squared equals 1 is a circle of radius 1. But since there's no z in that equation, z is basically allowed to do whatever it wants. So you can basically extrude the circle here. Okay, so that cylinder actually continues on in both directions. If you actually assemble all of this thing together to figure out, what total region overall I'm looking at, well, it should be flat on the bottom because we've got the xy plane. It should be cylindrical on the sides because of that cylinder. Okay, and again, this is radius 1 here. And then it should have this spherical thing on the top. Okay, so this bit up top, that's actually the sphere of radius 2, so this thing caps out at height 2. It's almost a cylinder, but it's round on top. Okay, so we do have a non-trivial region here for our E that we're looking at. Okay, so this is my region. Again, the thing that I want to evaluate is 2z times x plus 1 over this region. Now, I'm going to sort out my bounds first, right? Now that I know what this thing looks like. Okay? My z bounds, if I just wanted to try to take a look at this thing in terms of my standard triple integral setup, on the bottom, we've got the plane. Okay, so on my bottom, this is z equals 0. On the top, we've got that sphere. Now, I don't just want to give the sphere equation. We need this in the form z equals something. Now, if I scroll up real quick, we saw that sphere equation was x squared plus y squared plus z squared is 4. If you solve for z and you give the positive branch to make sure that you got the top of the sphere and not the bottom, solve for z there, that's going to give you your upper bound on z. Okay, so this would involve me subtracting off the x squared and y squared terms. That would give you z squared. You have to square root this to get z back. Now, catch, we're trying to do this in cylindrical. I can't leave the x squared and the y squared here. So these are the things that you actually need to replace, right? We can't leave my upper z bound looking like that. Z equals 0 is totally fine as a bound because there's no x's and y's, but this thing we need to fix. Now I mentioned that you could actually replace x's and y's with our cosine theta or our sine theta. Probably the faster way to accomplish this is, I'll show you guys a little trick. Think about this as 4 minus the quantity of x squared plus y squared. If we do that, I've already given you guys the shortcut. That's going to turn into 4 minus r squared. So we've really got that my z bounds here are going to be stuck between, let me get my character straight here, 0 and root 4 minus r squared. Okay. Now, you could, if you replaced x with our cosine theta and y with our sine theta, that's fine. That's totally fine. You'll just grind through the simplifications and get this in the end anyway. Okay? So we're just trying to save a little work. Now, that's just the z bounds. What about the x and y bounds? Again, keep in mind, the x and y bounds are going to come from this projection of this region to the xy plane. So if I'm trying to sort out my x and y or my r and theta bounds, well, the region that I'm worried about, since that cylinder was x squared plus y squared equals 1, this is just the unit circle that I'm worried about finding bounds on. Now, if this is the unit circle and I want r and theta bounds, well, hopefully it should be pretty clear. R here is stuck between 0 and 1. Okay, we go from 0 units away from the origin all the way out to 1 unit away from the origin. And if you want the bounds on your angle, we do go all the way around. So here my theta is stuck between 0 and 2 pi. If you were just dealing with a quarter wedge, you would have to pick the angles accordingly. So if we didn't go all the way around the origin, you would have a different range of angles. But anytime you do go all the way around the origin, you're stuck between 0 and 2 pi. Now, we've got my bounds straightened out. The next thing that we needed to do was fix my function, right? My function here, again, I will scroll up one more time just to give a refresher of what we were working with. This was 2z times x plus 1. Okay, 2z times x plus 1. I'll just make the note. This was the thing that we have to replace with our cosine theta, right? Anytime you see an x, replace it. Anytime you see a y, replace it with its corresponding function, okay? So now we're pretty much ready to go ahead and do the assembly for this, right? I said for my function, when we go to fix that thing, x's have to be replaced with our cosine theta. My differential on the end, it was initially dv. I now have to replace any differential on the end with r dz dr d theta. And now I've got the ordering set up for my bounds. We decided that z was supposed to be stuck between 0 and root 4 minus r squared. We decided that r was stuck between 0 and 1, and we decided that theta was stuck between 0 and 2 pi. If I go to evaluate this, I'll go ahead and scroll down to give myself a little bit of room. Comment number 1, all this stuff over here, the r, all of this junk, that's going to act like a coefficient on this 2z. Actually, the 2 is a coefficient too. But we're integrating with respect to z first, so really you're anti-deriving 2z, and the rest of this hangs on as a constant coefficient. Okay, so I'll go ahead and note your antiderivative of that is basically z squared times all the rest of this stuff. I'll go ahead and distribute that r through just for simplicity's sake. So your antiderivative looks like this guy, and we have to evaluate between z equals 0 and z equals this root here. Okay, and then obviously still deal with the rest of our integration that's happening. Now, if I evaluate, just a trick I'm going to go ahead and use, that constant coefficient, the r squared cosine theta plus r, this is going to be attached to both terms. So I'm just going to go ahead and hang on to that guy and factor him out of both of those preemptively. But, when you plug in the top and subtract off the bottom, we're basically getting the z squared. So 4 minus r squared squared minus the other z squared, so minus the 0 squared. Now if I go to clean that up a little bit, you'll notice that I am squaring a square root for the region that we are on right now. I'm not going to worry too much about signs. What you get back in that inside of the root should be positive. So the square and square root cancel. I basically just got a 4 minus r squared left over here that I now have to antiderive with respect to r. Now, I've got a product. I probably don't want to, antiderive this as is. Comment for evaluation here. What I would suggest that we do is actually FOIL this out before evaluation. So, first terms, I'm going to get 4r squared cosine theta. My outer terms, I'm going to get minus r to the 4th cosine theta. My inner terms, I'm going to get 4r. In my last terms, I will get minus r cubed. Now if I antiderive with respect to r, what I'm going to go ahead and get is 4r cubed over 3 cosine theta. The cosine theta is a constant coefficient here. Minus r to the 5th over 5 cosine theta. And the cosine theta is a coefficient here. And then on the end, I'll get a 2r squared. And also a minus r to the 4th over 4. Now, that was me antideriving with respect to r. We have r stuck between 0 and 1 here, and I know I have a whole bunch of terms, but thankfully, plugging in 0, all of this drops off. So really what happens is we're worried about what occurs when you substitute in 1. If you substitute in 1, you get a 4/3 cosine theta minus a 5th cosine theta plus a 2 minus a 4th. We can simplify this if you want. 20 minus 3 over 15, I should get 17 over 15 cosine theta here. 2 minus a 4th, that should be 7/4 on the end. And then this is a single variable integral, so this is a standard calculus 1, calculus 2 problem, okay? At this point, you should be getting 17 over 15 sine theta plus 7/4 theta evaluated between 0 and 2 pi. Well, comment, both of those angles are technically the same, so when you plug them into this first term, that's going to drop off. This is ultimately going to turn into 7/4 times 2 pi minus 0, or you should end up with 7 pi over 2. Okay. Now, comment, and I did want to close on another example here just to highlight this. I've done 2 examples so far where we're dealing with cylindrical sides, and I wanted to emphasize this isn't necessarily necessary for all of the examples that we'll do. We don't have to explicitly see a cylinder involved. The key thing is just that when you project this, or when you look at the shadow of your region on the XY plane, if it looks like a polar region, this is something that's tentatively okay to do with cylindrical integrals. So, as an example here, I'm not going to have us work out the whole thing. I'm just going to have us express this as a cylindrical integral. How do I rewrite this thing if I've got a region between a paraboloid and a plane? Now, refresher on what the paraboloid looks like. Talked about this eons ago, it seems like, but paraboloids just kind of look like these bowl shapes. And if I've stuck this region between a paraboloid and a plane, specifically a plane that's got a that's horizontal, z equals 4, this thing goes up 4 units tall. Here's my region, right? It's like a bowl with a cap on it. So, if this is my E, how the heck do I express this integral? Well, first thing I need to do is sort out my bounds on Z. Now, hopefully it should be pretty clear from the picture, but the paraboloid's on the bottom, the plane's on the top. So, we want to stick this paraboloid as the lower bounds and the plane as my upper bound. We can't leave it like that. right? If I'm expressing this as a cylindrical integral, we are going to need to fix my bounds, and fixing my bounds means replacing my x and my y correspondingly with r cosine theta and r sine theta, or I can use my shortcut, r squared. Okay, so my new bounds on z are gonna look like this guy. The next thing that I need to sort out are going to be my bounds on x and y, or r and theta, more importantly. So that means that I need to kind of project this guy down and figure out, you know, if this casts a shadow on the xy plane, what the heck shadow is that? Okay. Now, comment, what circle is this, right? I don't actually give you guys in the descriptor for this example something that explicitly looks like a circle. You know, there's no x squared plus y squared equals a number here. So I will go ahead and give you guys the refresher. We touched on this at the very, very end of the last section. If you are worried about the intersection between two surfaces, and here we are, you can set the functions for those two surfaces equal to find the curve of intersection. Now, here's what I'm talking about. You'll notice that this very, very top surface is my plane, and this bottom surface here, this paraboloid, meet in a curve. They meet on this curve at their intersection. And very coincidentally, I am worried about the shadow region, which looks exactly like the inside of the shadow of that intersection. So it would be helpful if I knew where the heck those things intersected, right? Now, like I said, what we want to do is set my functions for my surfaces equal to find that curve. Okay. Now, what surfaces am I working with? We just said the paraboloid and the plane. That's going to give me x squared plus y squared equals 4. So if I'm worried about which circle this is, we hopefully know at this point if it's x squared plus y squared equals 4, well, that's going to be the circle of radius 2. So if that is this circle, what that's going to force are some bounds on r. We're clearly stuck between 0 and 2. And theta. We go all the way around, so we're stuck between 0 and 2 pi. Now again, not all of your cylindrical or polar regions are always going to be circles. If you are more restricted than this, you'll get a different range of angles. But if you go all the way around, we're stuck between 0 and 2 pi. Okay? Now, we've basically got the bounds set up. I did have to do a refresher on the function. Remember, the function was x and y. We basically have to replace my x and my y. Okay, so x was supposed to be r cosine theta. Y was supposed to be r sine theta. Okay, that was how we fixed my function. Now I'm going to go ahead and get a setup with this integral. All right, so I'm going to leave myself a little bit of space here. If I fix my function, okay, my original problem appears right here. If I go to fix my function, I have to rewrite x and y. X is supposed to be r cosine theta, and y is supposed to be r sine theta. If I fix my differential, okay, my original differential was dv. We always replace dv with r dz dr d theta. You have to have an r as a conversion factor in here. If you leave it out, your integral is going to be wrong. Okay, so we've got the function, we've got the bounds. I need to get the integrand straight. We said earlier, okay, my bounds on z, they were right here. Z is stuck between r squared and 4, so that'll go right here. And my my bounds on r, my next variable, these are between 0 and 2. And my theta, we said this is between 0 and 2 pi. Now, a comment that I will go ahead and make whenever you do these replacements, if I needed you to evaluate this integral, I don't in this case, I just asked for setup. If I asked for you to evaluate this integral, please make sure that you simplify before you try to attack any of these things. Okay, this is a really poor setup for us to actually try cranking this out. If you wanted this to be a little bit more doable, clean stuff up first. Okay, so this guy in a nice, pretty, ready to go form for us to be able to tackle it if desired. This is probably what you want to work with. Okay, so this would be our setup for integrating XY over that given region in cylindrical.